Hello, class. We are finishing section 7.7, parametric equations. We will pick up with writing parametric equations. Example, write a pair of parametric equations that will produce a line segment starting at -2, 4 with t equal 3 and ending at 5, -9 with t equals 7. To work this problem, you must recall from Math 171 and your high school math classes that y equals mx plus b, the slope-intercept form of a line, and most importantly, the point-slope formula for writing the equation of a line, y minus y sub 1 equals m, which is the slope, times x minus x sub 1. Of course, first point gives the x sub 1 and y sub 1 values, -2 and 4 respectively. The slope is not provided, but of course you may calculate the slope since you're given two formulas using the slope formula, y sub 2 minus y sub 1 over x sub 2 minus x sub 1. So substituting in the point slope formula and then solving for y to have the equation in slope intercept form, you obtain y equals -13/7 x plus 2/7. This is the first equation, but notice that this equation is not in parametric form, because if it was in parametric form, we would have the variable either y or x, not both, and we would also have to have the variable t in the equation. But we need this equation to find our two parametric equations. So we're just going to hold on to this equation. Now, rewriting the slope-intercept formula and the point-slope formula for parametric equations. With parametric equations, we know our first variable is t, representing time, and of course the second one, x. So in our normal point-slope formula, where we have y, the second coordinate, second portion of the coordinate of a point in our rectangular system, we replace that with the second portion of the coordinate here, which is x. So y is replaced with x. Likewise, x, that first coordinate, is replaced with t. And that is done for both formulas, the slope-intercept formula and the point-slope formula. Now we have the point-slope formula in parametric form. So, plugging in our point, -2, 4, that was given, along with a value of t here in the parametric form. Precisely, we actually only need to plug in for x and for t. So plugging in -2 for x, 3 for t. Solving, our final answer is x equals 7/4 t minus 29/4. Please notice that in parametric form, our points are in the form x value followed by t value. So the points used to find the slope were -2, the x value, 3 for the second portion of that point, and likewise 5 and 7 to get the slope of 7/4. At this point, we have our first parametric equation. We know what x equals in terms of t. Now, completing the problem by finding out what y equals in terms of t. To do that, you go back and pick up the very first equation you found. That was a rectangular equation containing the points. And in place of x, you substitute what you just found x to equal in parametric form and simplify. After doing so, you find that y equals negative 13/4 t plus 55/4. And the problem is complete because we have our parametric equations. We know what x is equal to in terms of t and what y is equal to in terms of t. Looking at an application problem. This problem involves the parametric equations for the path of a projectile. So anything projecting the air. In that situation, because of the force of gravity, x equals v sub 0, which is the initial velocity, times the cosine of the angle times t. And y equals negative 16t squared plus v sub 0, the initial velocity, times the sine of the angle times t plus h sub 0, which is the initial height. And this time the height is calculated in feet. Our problem reads, an archer shoots an arrow with a height of an archer shoots an arrow from a height of 5 feet at an angle of inclination of 30 degrees with a velocity of 30 feet per second. Write the parametric equations for the path of the projectile and sketch the graph. So plugging in the equation for x, the initial velocity was 300 feet per second. The angle was 30 degrees. Simplifying by taking the cosine of 30 degrees, plugging that in, of course 300 divided by 2 gives us 150. So x equals 150 times the square root of 3 times t. Finding what y equals in parametric form by plugging into the appropriate equation, we get our angle. We have our angle to plug in once again, which is the 30-degree angle. We have our initial velocity to plug in once again, v sub 0, which is 300. We also have the initial height to plug in. This person was standing on an object that had a height of 5 feet. So 5 is plugged in for the initial height. Using the order of operation to simplify, we find that y equals negative 16t squared plus 150t plus 500. We have our equations for x and for y. So to graph, we plug in numbers of our choice for t into the equations and get values for x and also values for y. Notice when 10 is plugged in for t, the y value is negative 105. That's highly unlikely. So that basically tells us that the item has returned to the ground, that it's no longer in the air. Of course, if it was landing over a hole, this would be possible, or perhaps over the ocean, then, or lake. It could perhaps be in that situation land 105 degrees below the ground, but usually things are landing at ground level unless we're told otherwise. So looking at the graph, plotting these 3 points, I did not enlarge them, but plotting these and graphing. Of course, you can plug in any numbers you want to for t, so your points may be a little bit different. But here is the graph. We see the arrow reach that highest point and then begin to come back down. And this graph fits nicely with the points because we can see that when x is 2,598, it's below ground level. And looking at the graph, we can see a little before we reach, looks like 2,500. we're already at 0. The arrow is no longer in the air.